Welcome to this lecture. In this lecture, we will look at rational maps that are a generalization of morphisms between algebraic varieties. So the problem that we are facing is that algebraic geometry is all about understanding varieties via their regular functions. For affine varieties, this is great. An affine variety contains exactly the same information as does its coordinate ring. For complete varieties, the situation is worse. So in the completeness lecture, we saw that on a complete variety, there are no non-constant globally defined regular functions. On connected complete varieties, I should say. So what do we do about this? We want to allow more functions. The definition of a globally defined function is a bit too rigid, it seems. And so we will allow functions with poles and indeterminacies and things like that. Namely, we want to allow functions that are undefined on small problematic sets of our varieties. If you are familiar with complex analysis, think of meromorphic functions, functions with poles or functions with points of indeterminacies. If you're not, that is fine. More generally, we want to allow maps between algebraic varieties that are defined only on dense open subsets, that are not necessarily the whole set. As a bonus, we will see in forthcoming lectures that this gives us a way to deal with bad points and singularities. So let's get started. And let us start with the general notion of a rational map. So now we're not just looking at regular functions, we're looking at maps between algebraic varieties. So consider two algebraic varieties, x and y. And remember that our idea is to study functions defined on a dense open subset. And because of that, it's natural to study them up to equality on a dense open subset. Let's see what this means more precisely. So what we will consider are pairs UF, where U is a dense open subset of our algebraic variety X, and F is a morphism from U to Y. So remember, an open subset inherits the structure of a variety. It's an open subvariety. So a morphism, the notion of a morphism is well defined. And so this is what is meant by functions defined on a dense open subset. What does equality on a dense open subset means? It means that we view two such pairs as equivalent if the functions f and g in the pairs agree on some dense open subset in the intersection of u and v. So we have here u and here v. And if the functions agree on a dense open subset, then we view them as equivalent. So we identify more or less functions that behave in this way. And now a rational map from x to y is an equivalence class of such a pair, UF, where U is a dense open subset and F is a morphism from U to Y. An equivalence class with respect to the equivalence relation defined in the previous slide. And you can check that it is an equivalence relation. So if you don't like to view these rational maps as equivalence classes, just think of them as maps defined on a dense open subset, but with a more lax notion of equality, where two maps are equal if they are seen as equal if they agree on a dense open set. And in fact, the fact that this relation is transitive is due to the fact that if you intersect dense open subsets, you still have a dense open subset. If you intersect finitely many, so you are fine. The notation for rational maps is this, is writing f colon x dashed arrow y. And notice that I am writing f for the rational map. So I am picking one f from this equivalence class, and I'm also not including the u. And it will appear later why this is reasonable. So we really think actually about the map f. Everything else is there to make the construction well defined. And we say that f is defined at a point x if there is a dense open subset u prime and a map f prime giving us a pair in this equivalence class. So it is not necessary that the specific u that is connected to our f is where this x lies, but it might be some other dense open subset that is together with its map equivalent to the one we're looking at. So take a moment to digest this definition. Let's look at a few examples. Well, of course, any morphism f from x to y is a rational map. Just take dense open subset u equals x. So this new definition subsumes the definition of morphisms. Then you get the map, say, from P1 to A1. So there are no maps, non-constant maps, strictly speaking, between P1 and A1, but I simply map. So the idea is to map x to x for all, well, okay, let me be precise. What do I mean by this? x0 to x1. Say I map to x1 divided by x0 for all x0, x1 with x0 different from 1. So I forget about the point at infinity, simply, and I can take any dense open subset that doesn't contain the point at infinity. So in particular, I have a maximal dense open subset, which is the set of all x0, x1 with this property that x0 is not 1. And then it will be well defined. And also I can take, say, from A2 to A2, mapping xy to 1 over x, say. This is defined whenever x is not 0. So here you can see the added freedom that this brings me. And let's look at a few remarks that you might have thought about in the previous examples. So as a consequence of density, if you have two morphisms from some variety w to some variety y, well, in fact, w can be any pre-variety as long as y is a variety, then we have seen that the set of agreement, the set of all x in w where f and g are equal, is closed. And so therefore, these two maps are equal on all of w if and only if they agree on a dense open subset. Because if they agree on a dense open subset, they must agree on its closure, which by density is the whole of w. This is what you would expect from a set that you want to call dense. One other way to phrase it is that the restriction OW of w to OW of w prime is injective. This has some consequences. So remember, in our definition of rational maps, we had this equivalence relation. We said that UF is equivalent to VG if and only if, by definition, F and G agree on some dense open subset of the intersection. But because of this property, agreeing on a dense open subset of the intersection is equivalent to agreeing on the whole intersection. Secondly, each rational map has a representative with a maximal open subset. Simply take as this maximal open subset the union of all u's where uf is included in the equivalence class. Or if you wish, take the set of all points where f is defined. And so if you take this representative uf with u maximal open, then any other element in the equivalence class will be such that v is dense in u, because v is already dense in x, and g is the restriction of f onto v. So this justifies dropping the open set in the notation of a rational map, since we can always take the maximal open set and that f and look at all points where the rational map is defined at once. It doesn't make any change. So now, as a special case of rational maps, we look at rational functions. So remember that a regular function is the same as a morphism from x to a1. So this is a regular function on x. So by the same philosophy, a rational function should be a rational map to the affine line. And indeed, this is how we define a rational function. And the set of rational functions is denoted by kx. We can define sums and products of rational functions. So if you have a rational function f, well, say represented by uf plus vg, then on the intersection, because u and v are dense, so will the intersection be. So this is a dense open subset, and there you can define the pointwise sum. Because now both f and g are defined there. And similarly, you do with the product. And so it is easy to check that this is in fact a ring or a K-algebra of functions that you get in this way. The interesting thing is that if x is now an irreducible algebraic variety, then this Kx is a field. Pause and think why this is true. So the thing that we need to check is that every non-zero element has an inverse, right? So if you have, say, u phi, if this is an element of your kx, then 1 over phi is not necessarily defined on u, but it's defined on u wherever phi does not vanish. And this is an open subset, the complement of a closed set. And it is dense because our algebraic variety is irreducible. So since our phi is not identically 0, this set will be non-empty, and every non-empty open set is dense in an irreducible algebraic variety. So disregarding, and this captures what happened in the example of 1 over x, you can just make everything invertible by disregarding a small number of points. By small number, we mean closed set. And closed sets are very small inside irreducible algebraic varieties. So a few remarks. If you take such an irreducible algebraic variety and you take a non-empty open subset, so necessarily then a dense open subset, then k of u is isomorphic to k of x. It should be fairly clear simply if you have some phi here, then phi is going to be a regular function on some open v, in U. And then you map it to phi seen as an element in OX of V. And likewise here, given such an element, you take its restriction to U intersection V. And this is, again, a dense open subset. So we will be fine. The next remark is that this field Kx is the fraction field of the ring, the coordinate ring of any affine open subset U different from the empty set. So remember that X being an algebraic variety means that it has an open cover by affine varieties, and X being irreducible means that any such non-empty affine variety is dense. By the previous remark, it is enough to check the statement. So it is enough to check that K of U is the fraction field of OU of U when U is affine. But then K of U is the ring of functions that are locally invertible, and you can show that this is the localization of this OU of U at the zero ideal. So namely, it is the fraction field of OU of U. And in all these cases, irreducibility means that these things are integral domains. So this notation makes sense. Let us now look to an analog of surjectivity for rational maps. So as you can imagine, it is too much in this setting to require that a rational map be surjective. Rather, we want its image to contain a dense open subset. And indeed, a rational map satisfying this property is called dominant. Of course, this terminology can also be used about rational maps that are in fact morphisms. So dominant means that the image contains a dense open subset of the target variety. And so if X and Y are irreducible, then F is going to induce a pullback from the field of rational functions on Y to the field of rational functions on X. Simply, if you have Y to say let's say A1, phi, then you compose it with F, and this gives you F star phi. And because F is dominant, then you know that you will hit most of Y, so you can pull back phi to X. It will still be a rational map. It will still be defined on a dense open subset of X. And this means that we get some sort of functorial construction, and indeed the assignment that assigns to each variety its field of rational functions and to each map its pullback defines a contravariant equivalence of categories between the category of irreducible algebraic varieties, but where the morphisms are not ordinary morphisms but dominant rational maps, to the category of finitely generated field extensions of K. I will omit checking these properties, but the essence of this is that the field of rational functions captures the properties of an irreducible algebraic variety X, but not precisely, not up to isomorphism, but only up to dominant rational maps. And the reason why we know that these field extensions are finitely generated is that k of x, as we saw in the previous slide, is the field of fractions of some affine algebra. And so therefore it is a finitely generated field extension. This brings us to the definition